Welcome to Alaska Earthquake Science Facts. I'm Carl Tape. A thick block of Earth's crust is colliding with southeastern Alaska to form spectacular mountains, Chugach, Wrangell, St. Elias, including 14 of the 20 highest peaks in North America. Here's a photograph of 4 of those mountains. These are the Wrangells seen from near the Richardson Highway. On the right, we have the 5th highest peak in the US, Mount Blackburn. On the left, Mount Sanford, the 6th highest peaks. These are really big mountains and are not that well known in the US. Here's a view of Mount Blackburn from the southeast, looking up the Kennecott Glacier, 5,000 meter mountain, and you kind of get a sense of the ruggedness and remoteness from this photograph. St. Elias Mountains, this is the Fairweather Range, Glacier Bay National Park, and here you can see these spectacular mountains rising high above sea level, shown here in the foreground, Mount Crillon and Mount Bertha. Another view of Mount Crillon from the other side, looking toward the north. This shows Lituya Bay, which will come up in other Alaska science facts, but again, you can see these really large mountains very close to the coastline. Here's a shot of Mount St. Elias from Icy Bay, and at 18,000 feet and 11 miles from the ocean, this is the world's highest coastal mountain. So what is causing such high mountains so close to the coast? To look at these lists, just to say here are the highest peaks in North America, it turns out, as the fact states, there are 14 out of 20 are in the Wrangell St. Elias Mountains, either in Alaska or Canada. So you can see here Mount Logan, Mount St. Elias, Mount Luciana, and many other peaks, probably which are not familiar to everyone. So this is a special mountain range in North America and really in the world. We look at a subset of just the peaks in the US. We could see that 12 out of 13 are in Alaska, and 9 out of 13 are in the Wrangell St. Elias Mountains. So I'll provide an overview on some of the key history of our understanding of this region and how it fits in with plate tectonics, and I'll also show some of the key features that have been discovered in the last couple decades. So here's a map, 1978, George Plafker showing this Yakutat block. And this block is partly on land, partly offshore. So you can see the coastline right here, Yakutat Bay. And you see on the right, there's this Fairweather fault, which will appear in a couple other Alaska science facts. And this arrow shows that the Pacific plate is moving to the northwest here. So as the quote says, this implies that the segment of the continental margin bounded by these faults, informally termed the Yakutat block, is presently moving northwestward with the Pacific plate and is under thrusting the continental margin. That's what these little teeth mark on these lines indicate, that this block is going down under Alaska along the Pamplona fault zone and Aleutian megathrust. So here in 1978, we have the term Yakutat block. 1987, the perspective and description changed a little, and we see this usage of the word terrain. It's a geological unit that in many cases has come from far away, originated under different settings. And Alaska is made up of a lot of these terrains that have kind of crashed together over time. And we see here Alexander terrain, and the Yakutat terrain is another one of these. So we have the Fairweather fault on this FF on the eastern side, and then lots of these tooth marks showing one block going down under and thrust under. So this idea about terrains has been really nicely depicted in a couple different ways. And this was a puzzle made for a museum exhibit. This is made by Roger Top, where the user can kind of pick out these major terrains and move them in ways and think about how they piece together. But another piece from here is, where did they come from and when did they sort of adhere to Alaska? So here the arrow's pointing to this most recent one, this Yakutat terrain on the outer outer area. Another great example, though, is from the great Alaskan artist Ray Troll, and the piece is called Great Alaska Terrain Wreck. And to gain some understanding, we have to have some idea of what it really represents. Of course, the play on words is between train and terrain, but here each of these is named, and there's quite a bit of detail in this picture. For example, North America would be the barrier. That's what the train is wrecking into. And the oldest in the front, you'd have the older terrains, and in the back, coming in late, for example, the Alexander terrain coming in late. And I just assume that coming in even later might be out here as the caboose would be the Yakutat terrain crashing into this party at the very end. So a neat connection between tectonics and art. So one of the interesting things about this area is that it says there are young sedimentary rocks high in the mountains. This is a sign of active tectonics. Sedimentary rocks are deposited in oceanic or marine settings, and in order to get turned into rock and then thrust up into the sky and deformed, there needs to be some impressive forces happening at relatively short timescales, geologically speaking. So what we're seeing here, this photo from a figure by Chapman and others, northern Carr Hills looking west at the contact, this unconformity here, the boundary between Quaternary Tertiary Yakataga Formation right here. So Q meaning pretty young, a couple million years, but that's relatively young when you're looking at rocks in the mountains. And the Kuliath Formation, TK, shown right here. So here's the boundary between these units, but you can see these sedimentary rocks up in the thrust high, making these mountains a sign of really active tectonics in this area. And these are mapped in this geological map showing this Yakutat block. On the east, again, is the Fairweather Fault. And then as we go toward the northern side, we see these little teeth marks indicating that units are being thrust down and under Alaska. And the shaded regions, here is this Yakataga Formation shown right here, reminding us that these are relatively young rocks being thrust up to form some of the mountains. And so this is the coastline here, Malaspina Glacier, Yakutat Bay, and we will see what some cross sections through this look like. So here's one cross section on the eastern side. We see the Yakutat terrain on the southwest and the North American plate on the northeast. This is the Fairweather Fault, so we're kind of looking down in this cross section, and what we see is the symbol shows kind of like an arrow shaft, so looking down the backside of an arrow, and this is looking down the front of the arrow. So this is showing that the Yakutat terrain is moving to the northwest in this picture relative to North America. And you see a fairly straight boundary between these two units. And to confirm that this Fairweather Fault is a major boundary, there later in 1999, when GPS measurements were reliable enough, scientists measured 46 millimeters per year relative motion across this fault. As the authors wrote, the slip rate we estimate is one of the highest observed across any strike slip fault. And I think of it sort of as the northern San Andreas Fault. It's on this side of the Pacific North America plate boundary, only it's slipping quite a bit faster. And the San Andreas measurements about 36 millimeters per year, whereas 46 millimeters per year in this section. The other cross section looking to the north on this central segment, so this is from north right here and to the south, the Yakutat terrain is colliding with North America, and this is shown by all these thrust faults in here, with basically the Yakutat terrain being shoved down under North America and being quite a bit of resistance to that happening. So along the eastern boundary is a strike slip fault, and this block kind of moves toward the northwest, and this is what that contact looks like or is interpreted in cross section, with these shaded materials being these young sedimentary rocks such as the Yakataga Formation. So some questions that are asked at this point: how does the Yakutat block connect with the Pacific Plate offshore? What about the deeper part? Is it below Alaska? How did the Yakutat block form? And so we'll look at how scientists have begun to decipher these in the last 10 years or so. Here's a figure shown for a large active source seismic experiment where a ship is sent out into these regions to survey the geophysics of the seafloor and what's below. And in these experiments, you have an active source, acoustic source in the water that sends seismic energy down and comes back up and is recorded by things like ocean bottom seismometers along this line, or even by seismometers on land. So here we're seeing the same picture again of the Yakutat block or Yakutat terrain, the Fairweather fault, strike slip fault here, and we'll be looking at a cross section of the seismic image of what's below. And this will be a key piece of this story. Just want to point out too that the continental shelf, there's a big drop in the sea floor. So this block here has shallow water, and then offshore it's much deeper. It turns out along that line that the transition, what we see of the continental shelf at the surface dropping down, it's actually much, much stronger deep down in the earth. Deep down in the earth, what is seen is that the Pacific crust is some 6 to 7 kilometers thick out here. This line is at 11.5 kilometers. And at this boundary, the base of the crust steps from 11.5 to 31.5 kilometers. It's one of the largest steps I'm aware of in the world where you have such a large transition, a 20-kilometer step over such a narrow area, something like 10 kilometers or so. So clearly, the geophysical perspective is that this is a very different piece of material from what is here with the Pacific. Keep in mind, there's no plate boundary in this picture. All of this is moving together, more or less with the Pacific plate motion to the north-northwest. But what you see is that there's very different material suggesting a very different origin for the Pacific crust versus this thick Yakutat crust. And the authors emphasize this by showing two profiles. So this is showing the basically the elastic property of the material, one for the regular Pacific crust shown here in red, and one for the Yakutat crust shown in blue. The velocity is the compressional wave speed of the material inferred from seismic imaging. And what you can see is that it takes a lot longer for this Yakutat crust to get up to these high speeds and down into the mantle. And if we see here, the the thickness down to 8 kilometers for this Pacific crust and down to 32 kilometers for this Yakutat crust, it's a very different material between these two sections. And so the authors propose that they compare the Yakutat profile shown here in the thick blue line with other profiles of oceanic plateaus in the world, and basically say this looks like an oceanic plateau, a thick oceanic crust of basaltic and other material, some of them being large players in other collisions in plate tectonic history or are still active today. So that's a big mystery solved, I think, for the Yakutat crust, that this is an oceanic plateau. And then we'll see some of the consequence of trying to shove an oceanic plateau into a subduction zone. But before that, I wanted to just point out a couple other things. This is from study led by Lindsay Worthington and others, that there's a huge pile of sediments on the Yakutat microplate. This is showing you the time it takes for a seismic signal to go down and hit more crystalline basement signal. So it's going through all this different sediment. And we'll look at a cross section. Again, same view, Fairweather fault, and then the collision happening in this region. We'll look at a cross section along this dotted line. And what is shown here is this wedge shape of the underlying basement, so the hard crystalline rock of this Yakutat crust. And here you can see there's up to something like over 10 kilometers of sediment that is getting shed off of off of mountains and other regions on top of this area. And this is what's going into this northwest direction, the direction of the Pacific Yakutat motion. This is being shoved into this collision zone. So this is a piece definitely of trying to understand what this block of material is. It's very thick, but it also has a thick cover on top of this basement. Leading to the question of what's further down, what can we not see from this Yakutat block? And this is an earlier paper in 1985 where one author was trying to piece together this story and was speculating that here's this Pacific plate. In this case, it's a south to north cross section. But here's this kind of normal Pacific oceanic crust, and then something thicker, not nearly as dramatic as what they discovered in 2010, but showing this thicker material, and importantly, suggesting that this is descending down, being subducted under, in this case, the Chugach-Wrangell terrain. So this is sort of saying, you know, this looks like a cross section of a collisional zone and implying that this over thickened profile is being subducted. And we will see that some of that is borne out. So here, looking in central Alaska, quite a bit farther away from Yakutat. So here's this Yakutat as it appears at the surface. An experiment in the late 1990s, early 2000, was able to image the slab going down under Alaska. And this shows some earthquakes that are known to delineate that this slab of Pacific is going down central Alaska. But what these authors found and revealed was that this oceanic crust is anomalously thick. It's much thicker than you'd expect for a regular subduction zone, and essentially proposed that this signature of thick crust is connected to the thick block that is offshore, that this is a sort of subsurface extent of the collision of the Yakutat block with Alaska. And another picture clarifying that in 2006 from a seismic imaging study, this shows the author's interpretation of where that Yakutat slab, because we're looking at both the subsurface expression underneath Alaska, in addition to the part that appears at the surface that we've been looking at earlier. But now we're having a bigger picture, which is this is just part of the story, and much of the past story shown here at 5, 10, 20 million years ago, trying to understand where back in time was the sections that are now under Alaska. So we're getting a bigger picture of this Yakutat block in that part of it is underneath Alaska now. To sort of culminate this discussion between what is subduction to the west, Worthington and others inferred that toward the west, there's more subduction style occurring where the Yakutat is able to go under North America, perhaps due to the thinner crystalline section of the material, whereas to the east, such as where Mount St. Elias, this very high peak in the St. Elias ranges, this is just true collision and will be continuing to resist. So this sort of transition from the west, certainly much farther west, we have regular subduction, but there's some transition between collision and subduction. I'd probably suggest for the sake of this material that this kind of over thickened crust, even if some of it's going down, is predominantly collision, and that's giving rise to these mountains. Where else do we see something like this in the world? Well, there's a famous example, much more famous than the Wrangell, St. Elias, and Yakutat, and that is the collision of India with the Eurasian plate. And this shows where India was relative to the Eurasian plate 71 million years ago, 55, 38, 10. And India is a continental crust that is crashing into Eurasia. And lo and behold, we find the highest mountains on the planet. And I really like this figure taken from a paper by Searle and Trillar in 2019, which has the space shuttle, giving us a reminder of the scale of these processes. Plate tectonics is large scale. And so to be able to view from the space shuttle or Google Earth and be able to delineate where are these main boundaries. So here, this is India to the west, Tibet, Himalayan plateau to the east. So India's crashing from left to right here. We see greater Himalaya, so that would include Mount Everest, highest mountain on the planet. And these would be the plate boundary or the thrust features where India is trying to subduct but resisting heavily going under the Eurasian plate. So this is sort of the view of a more famous example of active collision on the planet and the mountains that arise from them. So our analog here, and proposed even as early as 1983, this is Alaska up here, the present day configuration of, at the time, was the Yakutat block, but we've seen is probably partially under Alaska now. Where it was 5 million years, 15, 25 million years ago, the idea is that this terrain, as part of the terrain wreck, is coming from a long ways away, and that through this collision and resistance has formed these spectacular mountains. So this is a view taken out of an airplane looking toward the south. So far in the distance, you want to imagine the Pacific and the Yakutat block coming at you in this picture and colliding somewhere between the foreground. There's the North America plate, and in the background of the Pacific plate. And in that process of collision, these mountains are rising. So this is our analog for the Himalayan collision that's active today. The Yakutat collision with North America remains active in Alaska. So the takeaway topics: thick crust, like greater than 10 kilometers, resists subduction. Most oceanic crust is 6 to 7 kilometers thick. The Yakutat collision in Alaska forms the Wrangell-St. Elias Mountains. It is analogous to the ongoing collision between the India subcontinent and Asia, which forms the world's highest mountains. Young sedimentary strata thrust up above sea level and tilted is a sign of active tectonics. We saw that from the geological photo. Things have to be happening relatively quickly to get that kind of deformation. And lastly, I didn't talk much about earthquakes, but the collisional zone produces shallow dipping thrust earthquakes, such as in 1979, magnitude 7.4 St. Elias earthquake. And it also produces earthquakes on steeper dipping thrust faults onshore and offshore, such as the 1899 magnitude 8.1 Yakutat earthquakes. That's a topic for another science fact. And I'm not even mentioning on the east boundary on the Fairweather fault, where we have the Lituya Bay earthquake and strike slip faults. So thank you for watching, and stick around for some supplemental material. Wanted to thank Ray Troll for providing the image and allowing uh, use of it here in this lecture. One point about Mount St. Elias being the highest coastal mountain in the world. How can we justify this? One blog, The World's Biggest Mountains by the Sea, calculated slope times elevation as a proxy for this competition and found that St. Elias was number 2, with number 1 being Mitre Peak in New Zealand, which is 1,683 meters. Well, I took the liberty to just add a qualifier that the minimum allowable elevation is 2,000 meters. Otherwise, we're going to be splitting hairs with some very small peaks near sea level. So Mount St. Elias is clearly a spectacular mountain arising from the collision between the Yakutat Pacific and North America.